We present manipulation by feel, touch-based control with deep predictive models. Tactile sensing is critical for dexterous manipulation tasks and more physically immediate than other sensor information. However, effectively utilizing tactile sensing for object manipulation skills remains a major challenge. Modeling and characterization of tactile sensors typically requires delicate calibration and careful system identification. The goal of this work is to build a framework for learning how to perform tactile surveying without external supervision. We propose Tactile MPC, a method that leverages a deep recurrent neural network trained to directly predict future tactile observations, to control a robot to reach user-specified tactile goal states. A gel site sensor captures rich information about the contact states, including shear forces, surface texture, and many higher-level features. To train the deep dynamics model used in Tactile MPC, we use 7,500 trajectories with the ball bearing applying random actions, requiring no human supervision. Our deep dynamics model is a recurrent neural network that predicts future sequences of tactile observations, conditioned on sequences of actions and a starting image. At test time, the user specifies a tactile goal state. Using the model, we then find appropriate action sequences, replanning at every time step. Here, the task is to roll a ball bearing with the goal of reaching a user-defined goal tactile image. At each time step, the planner samples 200 candidate action sequences and ranks the resulting predictions by their distance to the goal image. On the right, we show the predictions for the 3 best action sequences found. Here we can see the trajectory actually taken by the robot. Now, we're showing another example for the ball bearing task. The second task is to maneuver the end effector in X, Y, and Z directions to reach a desired contact state with the analog stick, specified as a tactile image. To solve this, Tactile MPC must intentionally break and re-establish contact with the analog stick, requiring multi-step planning. This is an example of random data collection with the analog stick task. We collected 3,500 trajectories fully autonomously. In the tactile predictions, we can see that the model predicts breaking and re-establishing contact. We can see that the planner breaks contact and successfully reaches a tactile state close to the goal state in the end. Here is another task that requires lifting the sensor off the analog stick and touching down at a different location. The planner again breaks the contact several times and successfully reaches the tactile goal state. Our results show that Tactile MPC significantly outperforms hand-designed baselines on both the ball rolling and analog stick task. This is reflected by the median distance between the hand-annotated pressure centroid of the final tactile image and the goal tactile image. In this work, we took a step towards integrating rich tactile sensing with fine-grained robotic control, leveraging deep predictive models.